This is problem 2.56 on page 51. A sailor is being rescued using a boatswain's chair, I suppose that's how you pronounce it, that is suspended from a pulley and can roll freely on the support cable ACB and is pulled at a constant speed by cable CD. Knowing that alpha is 25 degrees, that's an angle, and beta is 15 degrees, another angle, and that the tension in cable CD is 20 pounds, determine A, the combined weight of the boatswain's chair and the sailor, and B, the tension in the support cable ACB. The figure may be useful. We take the pulley as a point, the sailor and boatswain's chair, I believe is what it's called, are applying some weight downward. They're being pulled down by gravity. There is a line, ACB, because this is point C. There's a line, or a cable, and I should, I guess, make a solid line here, where the angle of the cable on the left side is the angle alpha, 25 degrees that they gave us, and from horizontal on the right hand side the angle is the angle beta, 15 degrees. Now force B is here, or I should say tension B is here, and tension A is here. Now there's a pulley that rolls on it, but there's also force on the center of that pulley, pulling that force upward, or pulling the pulley upward, with a force D, which is equal to 20 pounds. And we're supposed to find out how much is the combined weight of the sailor and the chair, and also what's the tension. Now here's a key thing. The tension in the rope on either side, or the cable, whatever it happens to be, is the same, because this pulley is just rolling on these two. So the tension, as I've drawn it, TA equals TB. It's important that you realize that. And I'll just call this TACB, the tension in the cable ABC, or ACB, however you want to look at it. So to find the weight, what I'm going to do is sum forces in the horizontal direction. Well, instead of calling that TB, let me just call this force B and this force A. That'll mean less riding. So there's going to be a horizontal component of the force in the cable at B, just as there will be a horizontal component of the force in the cable at A, and there is a horizontal force, or a horizontal component of force D. Notice I'm using a typical right-handed coordinate system as follows: x to the right, y up. Thus, Bx is positive, Ax, Bx are both negative. But those are the only forces that act in the horizontal direction. Now, Bx can be written as B multiplied by the cosine of 15 degrees, because that would give me the horizontal component of B. A, on the other hand, can be written as A times the cosine of 25 degrees. And then, let's see, I've also got, let's see, here it is, the 20 degree, or 20 pound, so minus 20 pounds, times its angle. Well, that's also at an angle of 25 degrees, so cosine 25 degrees. This has to come out to zero. It has to be in equilibrium. Now, notice that I also said that the tension in A and B are equal, so I can actually take these two, factor them out, just call it TACB, multiplied by cos 15 degrees minus cos 25 degrees, minus 20, well, let's move that term to the other side, equals 20 pounds multiplied by cos of 25 degrees. And you can see that calculating the tension in cable ACB is pretty easy. It's 20 pounds multiplied by cos 25 degrees divided by cos 15 degrees minus cos 25 degrees. When you plug all that into your calculator, you find the tension of the cable's about 304.04 pounds. So fairly high force by comparison to the pulling force that's acting on the pulley. Now what about the weight of the boatswain chair and the sailor? Well, for that we sum forces in the vertical direction. So notice in that case we'd have a y pointing up plus by pointing up plus dy And all of those forces point upward except the weight points downward. So minus weight, that sum has to come to 0. We already know that A and B have the same magnitude. So let's write TACB. And how would we get the y component? Well, for AY, we'd use the sine of 25 degrees, and for BY, we'd use the sine of 15 degrees. Now, dy would be the magnitude d, which is 20 pounds, multiplied by the sine of 25 degrees. And that will all equal the weight. What I've done is just move the weight, pardon me, all I've done is move the weight to the other side, you see. Since we already know the tension in the cable, we can simply plug that in. If you haven't written anything down wrong at the board yet, I think we're okay. Plug that tension in for the variable here, 304.04 pounds, and calculate the weight. When you do that, the weight comes out to about 215.64 pounds. So now we know the weight of the sailor and the chair he's sitting upon, and we know the tension in the cable that's supporting the whole thing.